Okay, so today we'll solve two questions from real analysis. One is question number 43 from Gate 2019 and the other one is question number 13 from Gate 2023. Okay, so let's first start with question number 43. Okay, so today we'll solve Gate 2019 question. This is a question from real analysis. This is question number 43. It is saying that let 1 less than equals to p is strictly less than q is strictly less than infinity. And two statements are given. Little lp is subset of little lq, where little lp is the sequence space such that pth summable, it's pth summable. And the second one is the capital LP over 01 is subset of capital LQ01, where capital LP spaces are the Lebesgue spaces such that pth integral is finite. So these two are, we have means two statements are given. You have to, four options are given. You have to check which one is correct. Okay. So this is the NPTEL reference. This you can check. Okay, so let's start solving this one. So 1 less than equals to p strictly less than q strictly less than infinity. So 1, so we will show this. The first one is correct. We will show LP is subset of LQ. What is LP? Let me write. LP is the sequence space. So either summation n equals to 1 to infinity mod xn to the power p, this should be finite. And for any x in LP, what is the norm? Norm x small LP is defined to be n equals to 1 to infinity xn to the power p to the power 1 by p. So in order to solve this one, that LP is subset of LQ, it is enough to show that LQ norm of x is less than LP norm of x. Right? Why? Because if x is in LP, as if x belongs to LP, which implies this norm will be finite, which implies by this inequality, if this is finite, then this will be finite. So means x is in LQ. Which implies x is in LQ. So this implies, we have started with the LP element, we have shown that this is in LQ, means LP is a subset of LQ. So it is enough to show this one. Now observe on that this one is scaling invariant. So if you suppose multiply some numbers lambda, then it is cancelled from both sides. So due to this scale invariance, we can assume that LP norm of x is again means norm 1. Right? So dividing both sides by norm xp, we can assume norm XLP to be 1 and enough to show norm XLQ is less than 1. So this is we can assume that for x which is norm 1, for that norm x LQ norm of x is less than equals to 1. So now as norm x LP is 1, which means n equals to 1 to infinity xn to the power p is 1. So if summation of all the terms to the power pth power is 1, which implies xn is less than equals to 1 for all n, because these are all mod are all positive numbers. So if total sum is 1, then each terms will be less than equals to 1. Now as each term is less than 1, now as p is less than q, is strictly less than q, so q is bigger, so if you take the qth power, because this is less than 1, so this will be less, right? Now take the summation over all n equals to 1 to infinity xn to the power q, so this will be less than, right? And so what is this? So this is the basically LQ norm to the power q. This is xn x to the LP norm of to the power p, and we know this is 1. So what we have got, LQ norm of x is less than 1. So this we have to prove, right? So you have got this one. So therefore means little LP is subset of little LQ for 1 less than p, strictly less than q, strictly less than infinity, right? So first one we have shown. Now for capital LP, so we have to show that capital LP, but this we have shown the second one is not correct. For 1 less than p less than q less than infinity, capital LP of 0 1, this does not subset of LQ01. What is LP spaces? So this is all functions which are measurable, Lebesgue measurable, such that integral 01 mod fx to the power p dx, this is finite and f is Lebesgue measurable. So we will show that LP does not contain in LQ. So you will give a counter example. So these are Lebesgue measurable functions. So let's take fx to be 1 by x to the power 1 by q for x in 0, 1 and 0 for x belongs to 0. This may not need to define because Lebesgue measurable functions are defined almost everywhere. So like this, I am only writing this because this is defined almost everywhere sense. So now let's calculate what will be the pth norm. 0 to 1 fx to the power p dx. So 0 to 1, this will be dx by x to the power p by q. And we know p is strictly less than q. So what will be this integral? 0 to 1 x to the power minus p by q dx. So this will be x to the power minus p by q plus 1 by 1 minus p by q. This is from 0 to 1. So if you put, you will get 1 by 1 minus p by q. And as p is less than q, so this is finite as p is less than q. So as the pth integral is finite, which implies f is in LP 0, 1. So this is in LP. Now let's check, is this in LQ or not? 0 to 1 mod fx to the power q dx. So this is 0 to 1, fx is 1 x to the power 1 by q, so this is a dx by x. So integral is 1 by x, integral is log. But this is not convergent, this is infinite. So this is not finite. So f does not belongs to LQ. So we have find out an example which is in LP but not in LQ. So then therefore this cannot be true because this function is in LP but this is not in LQ for p strictly less than q. So therefore for 1 less than p strictly less than q less than infinity, LP 0, 1, this is not subset of LQ 0. This you can show that for 1 less than p less than, this is the other way around. 1 has LP 0, 1, one can show, or LP AB over some compact is this. So therefore this one is not true. So what we have got therefore? So 1 is correct, 2 is incorrect. So which one is correct? B only. 1 only is true. Okay. Okay. Okay, so we have done question number 43. Any question? Okay, so let's move to the next one. Okay, so today we'll solve Gate 2023 question. This is a question from real analysis. This is question number 13. It's given that let px, this is a trigonometric polynomial given 1 plus e to the power 2 pi x plus 2 into e to the power 3 pi x, pi I x. For x belongs to real number and I is the square root of minus 1. Then we have to find the limit of this quantity. It is limit n tends to infinity 1 by n, summation k equals to 0 to n minus 1, p of k root. Then 4 options are given. You have to find which one is correct. Okay. So in order to solve this, this is the NPTEL reference. This you can check. Okay, so let's try to solve this one. So this question is related to the equidistribution of a of sequence in certain intervals. So let me first recall the definitions. So a sequence n of real numbers is said to be equidistributed on a interval so non-degenerate AB if for every subinterval C comma D of AB we have so limit n tends to infinity. Take the first n numbers from the sequence a1 dot 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 an, intersect with that subinterval CD, and so this is meaning the numbers of the how many numbers from the sequence, first n numbers from the sequence lies inside this subintervals, means intersection with this subinterval. So this count the number of the points divided by n. So this should give us d minus c by b minus a, right? So this means that if this happens, then we say that this sequence is equidistributed on the interval AB. So for that you have to take the first n numbers from the sequence, intersect with the subinterval, and for every subinterval CD, find the number of points and then divide it by n and find the limit n tends to infinity. If this is d minus c by b minus a, then we will say that some sequence is equidistributed on an interval AB. Now we need equidistribution modulo 1. So when we say, so this is again a definition. So this is equidistributed on an interval, and a sequence of real number n is said to be equidistributed modulo 1 if the sequence of the fractional part, if the sequence of the fractional part of n, so this is n minus the integer part of n, is equidistributed in the interval 0, 1. So we say that a sequence of real number is equidistributed modulo 1 if the corresponding fractional part sequence means n minus the integer part of n is equidistributed in the interval 0, 1, because the fractional part always lies in 0, 1. Right. Now we need two theorem. So this is equidistribution theorem. Equidistribution theorem. So this gives necessary sufficient condition of certain sequence when this will be equidistributed. So the sequence of multiple, so the sequence of multiples 0, alpha, 2 alpha, dot 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 of some real number alpha is equidistributed modulo 1 if and only if alpha is irrational. So what it is saying? That a sequence 0 alpha 2 alpha, this sequence is equidistributed modulo 1 if and only if alpha is irrational number. Right. So this is the equidistribution theorem. So like for example this k root 2, if you take k belongs to natural number, is equidistributed modulo 1, right? Equidistributed modulo 1. Now we need one more theorem. This is Weyl criterion. Weyl criterion. So what it is saying? That a sequence n is equidistributed modulo 1 if and only if for all non-zero integer L limit n tends to infinity 1 by n summation j equals to 0 to n minus 1 e to the power 2 pi I L aj is 0. So this is Boyle criterion. So it is saying that a sequence an is equidistributed modulo 1 if and only if limit of this 1 by n summation j equals to 0 to n minus 1 e to the power 2 pi I L aj is 0. So we'll use this one to prove our problem. So we'll solve our problem using this one. So here what we have in the problem, so what is the problem? Here we have px is given by 1 plus e to the power 2 pi I what x plus 2 into e to the power 3 pi I x, and what we have to find? To find summation n k equals to 0 to n minus 1 1 by n limit n tends to infinity p k root 2. So means limit n tends to infinity. So this we have to find, right? So p, if you put p k root 2 e to the power will be, so let me write. So what will be this? 1 by n summation k equals to 0 to n minus 1 p k root 2. So 1 by n summation k equals to 0 to n minus 1. So it is 1 plus e to the power 2 pi I k root 2 plus 2 to the power 2 pi I 3 pi I k root 2. So for the 1, if you sum it, there are n number terms. So this is 1 divided by n. So it is 1 plus summation 1 by n k equals to 0 to n minus 1 e to the power 2 pi I k root 2 plus 1 by n. So this is 2 by n summation k equals to 0 to n minus 1 e to the power 3 pi I k root 2. So this I am writing it in different way. 2 pi I k 3 by 2 root 2. So now note that what is this? Limit n tends to infinity, what will be this? We know what we know from Boyle criteria, that if certain sequence is equidistributed modulo 1, then this kind of limit will be 0. So what is this here? So here we can take L to be 1 and this sequence k root 2. So if k root 2 is equidistributed modulo 1, then this limit will be 0, right? And we have proved earlier by the equidistribution theorem shown that if k root 2, this type of sequence are equidistributed modulo 1 because it is multiple of root 2, because this is given by the equidistribution theorem. So k root 2 is equidistributed modulo 1. So therefore, as k root 2 is equidistributed modulo 1, so by Boyle's criteria, one by n limit n tends to infinity summation k equals to 0 to n minus 1 e to the power 2 pi I k root 2 is 0. Similarly, you can show the next term because 3 by 2 root 2 is again equidistributed modulo 1. So by Boyle criteria, you get this. Similarly, we have limit n tends to infinity 1 by n summation k equals to 0 to n minus 1 e to the power 3 pi I k root 2 is 0. So what we have got? So both the term we have become this means this and this goes to 0. So only remain one term. So therefore limit n tends to infinity 1 by n summation k equals to 0 to n minus 1 p k root 2 is 1 because only 1 is remaining, other two term goes to 0. So this we get 1. Therefore which option is correct? Option number B is the correct one. Okay. Okay, so question number 13 is also done. We have solved both the questions. Any doubts?
हेलो ना व्यस्त में बोलो
Okay, bye.